Let's do it. We have equations 1, 2, 3, and 4 perfectly labeled. I'm going to read straight from the book. I'm just going to teach. They constitute a set of coupled first-order partial differential equations for E and B. They can be decoupled by applying the curl to 3 and 4. This is in vacuum. And in vacuum, the first one becomes del dot E equals 0. Because in a vacuum, there are no electric charges. So 0 times 1 over epsilon naught is 0. Also in vacuum, there is no electric current density. So mu naught J goes to 0. So then you have del cross B equals mu naught epsilon naught dE dt, vector, vector, vector. You curl 3 and you curl 4, and then apparently it just falls out. So let's do it. Our third Maxwell's equation, del cross E. I don't know if you can see any of this. Should I do it in a funky color? I'm gonna do it in a funky color. Is blue easier on the eyes or red? I think red is like alarming. You're like, oh my God, what's going on? Do it in red, blue. Del cross E equals del cross E is minus dB dt minus dB dt. We're taking the curl of the third equation here. These are partial spatial derivatives. This is a partial time derivative. You can interchange them, I think. So I'm going to do that. Bring out the minus sign. Bring out the d dt minus d dt of the curl of B. Vector, because why not? The curl of B is one of our Maxwell's equations. That's minus d dt. The curl of B is, in this case, because we're in the vacuum, it's just mu naught epsilon naught. Mu naught epsilon naught dE dt. Okay, so we have these constants. These are just coefficients right now, so we can move them out of these parentheses and out of the derivative. Keep the minus sign out here because why not? There might be a reason why not. Move these out, minus sign. We have another d dt, so we have d squared dt of epsilon of E. What the hell am I doing? You also need, this is more complicated than I thought it was. I mean, it's not. You also need this identity, right? I did this immediately, but my book is telling me that the curl of a function is the hell is this? Derivative times, what is this called when you apply it to a scalar? The gradient. Multivariable calculus is so important to me. The gradient of the divergence of the vector field, vector function, minus del squared, I don't remember what del squared is called, E. So then this is also equal to del gradient of del dot E minus del squared E. This is one of our Maxwell's equations. This is Maxwell's first, and a vacuum is 0. Haha. So now we have minus mu naught epsilon naught d squared E dt. I forget how to say this. D dt squared E, d squared dt E. The second time derivative of E equals 0 minus. So I'm going to bring this over here and drop the minus signs. Del squared E equals minus mu naught epsilon naught d squared e dt squared. Should I do the fourth? I forgot to put in earrings. I hate it here, bro. To get it for magnets is just as easy. It's like the same step, so I'm not even gonna do it again. I'm just gonna write the result. I don't know if this is good or usable. I didn't intend to use this in the video. D squared B equals mu naught epsilon naught D squared B dt squared.